kind of summarizes it very well. Thank you. First of all, thank you very much for inviting me over. I consider it a great honor to be speaking at this venue. I really appreciate it. Thank you very much. Okay, so the topic today is bias reduction in production speech models. It's a fairly specific and also highly vague title, but let's get into it and see where it goes. Okay, the story of deep speech and probably of all end-to-end models is this: find a model that fits your data set, your small data set or your target data set really well, and then scale. Scale both your models, your model size, as well as your data set size, and then you'll see curves like those in the right. As you increase your model size and increase your data set, your final metric will start improving over time. Except at scale, you run into problems that simply cannot be handled by adding more parameters or adding the specific kind of data you want. It becomes fairly prohibitively expensive. And then you really run into the bias of the model. You really start observing what biases the model is encoding and how this is stopping you from improving your model. Some of these examples are already seen in neural machine translation. For example, for handling rare words, people try to have a specific layer that copies a token from the source sentence to the target sentence. There's nothing really preventing your neural machine translation from modeling this transformation. However, it doesn't seem like something it learns even at scale, even as you add more parameters. Similar solutions have been proposed for handling long-range context, for handling or for enabling open vocabulary translation. In this talk, we'll see what kinds of issues we saw when we were scaling deep speech model and what kinds of biases were implicit in the model and how we fixed it to get it into production. All right. So this is, as of right now, this is unpublished work. We have a draft in the works, and we should be putting it on archive soon. All of this work is done by my teammates at Baidu Silicon Valley AI Lab. My name is Sanjeev Satheesh. I'm leading the speech team at Baidu's Whale, and these are the best pictures I could find from of my team members. It also includes a dark person who mysteriously is able to not have even a single image of him on the internet. So there's like a blue bar there. Okay, so the outline will be like this. We'll first talk about the deep speech model and what problem it is trying to solve. Then we'll get into how what kinds of issues we see and how we are trying to remove it. The biases are implicit in all levels of the model, in how in what laws we use for training the model. The biases are also implicit in the layers and in how we all the pre-processing steps that we do during inference. Okay, the deep speech model is basically trying to solve speech recognition, the speech recognition task, where your input is some audio clip and the model is trained to output what the person in the audio clip is trying to say, just plain text transcription. In a little bit more detail, the deep speech model is basically a deep neural network which takes in the spectrogram. It can be linear spectrogram, MEL spectrogram, whatever. It uses a few layers of 1 or 2 2D convolutions to read in the spectrogram, followed by a bunch of recurrent layers for modeling the speech and how to transform it to text. At the top of all of this is a softmax over your alphabet. This is perhaps the more interesting part of the model, is that you transcribe your output space is the alphabet of your language and an extra token called the blank. We'll get into that soon. So this model is trained with a single loss function called as connectionist temporal loss, which is often abbreviated as CTC. As a quick show of hands, can I see how many people know CTC or have heard of CTC before? Okay, so I'll give a quick overview of CTC also. So CTC is a maximum likelihood loss. It's just like cross entropy loss, right? Where you're trying to increase the likelihood of your correct answer of the label. Except you have to do this over a sequence. Your output space is a sequence. It's trivial in cases where your input sequence and your output sequence are the same length. But in speech, this is not the case. Often your audio sequence is much longer than your label sequence. So how would CTC handle this? CTC handles this by marginalizing over all possible expansions of the label sequence. Let's look at an example. Let's say your label is just the word cat, C-A-T, right? You want to find out what the probability of cat is, except you have 10 time steps where at each time step you have a probability distribution over the alphabet, right? What CTC does is it marginalizes over all alignments. An alignment is basically, you can think of an alignment as an expansion of the string that matches this, all strings that match this regular expression. This regular expression says CAT can be expressed as 0 or more blanks, followed by 1 or more C, followed by 0 or more blanks, followed by 1 or more A, followed by 0 or more blanks, followed by 1 or more T, followed by 0 or more blanks. Okay? And there are there's a combinatorial number of strings that match this regex. And basically, CTC calculates P of this label by basically summing over all possible alignments. It looks really expensive, but it's really cheap to do using dynamic programming. Is this somewhat clear now? Okay. Please feel free to interrupt with questions. We'll try to see what issues are there in this model, and we'll try to fix it. So it's important to get a sense for how this works. Okay. Of course, the original Deep Speech 2 model, which I mentioned earlier, had a bunch of bidirectional recurrent layers, right? All of these, there are like 5 or 7 layers of bidirectional recurrent layers. But speech recognition is a streaming problem. That is, people want the text as soon as they finish speaking. And if you put a bidirectional layer in there, you cannot get an output within 100 milliseconds of a person finishing speaking it, right? So what we want to do is replace all these bidirectional layers and see what's the best we can do with forward-only, with only unidirectional layers, with forward-only layers. So we did some hyperparameter and architecture search over it, and we were able to remove a whole bunch of these bidirectional layers and replace it with a small number of GRU layers. And the bidirectional layers also include information from the future, right? You cannot completely ignore that concept. So what we have is a 1D convolution on top, so that it looks at some information from the right. Sorry. Oh, a GRU cell. So are you familiar with RNNs? Okay. And RNN basically has 2 inputs, one from below, which is the input, and one is state from the previous time step. A ReLU RNN is basically that. It has 2 inputs, and it creates a new state. A GRU is a slightly more complicated version of that. It's trying to solve a specific problem called as vanishing gradients or exploding gradients. The thing is, these RNNs are unrolled over time. Let's say if your audio clip is 10 seconds long, you'll run your RNN up to 10 times however you're striding, right? Often what happens is when you calculate the gradient with respect to an RNN that's unrolled so many times, your gradient will often vanish or explode, and you cannot train your models anymore. A GRU cell is specifically trying to solve that problem. The details are, we can look it up in the paper. I don't have. It's still recurrent. It still has the same properties. It has 2 inputs, one from the input and one from the previous time step. It's just the activation is slightly different. Yes?
So basically the whole 5 layers to make it more completely kind of milliseconds layer. It will change the parameter.
Yes. More than the 7 to 3 transformation, the more important higher level bit is that we remove bidirectional layers and replace it with forward-only layers. The bidirectional layers, to run a bidirectional layer, you need input until the final time step because, forward-only models can be run in a streaming fashion. As you have small packets of audio, you can calculate the RNN as you get them.
LSTM would be a group, like
Yes, an LSTM is a GRU is basically a simplified version of LSTM. I should have just called it LSTM. Yes, yes. It's a slightly more simplified, so we are able to train bigger models than LSTMs. Yes. Cool. Everyone with me so far? Okay. All right. Cool. So what happened? So we are in this graph. This is a. I wish this were a table. I'm sorry about that. We are measuring the word error rate on the training data, which is we are trying to see how well this model understands the training data. Okay, so word error rates, so smaller is better, closer to 0 is better. The baseline bidirectional model has something close to 7 WER, so it fits the data reasonably well. The best forward-only model you could train has a word error rate of over 12. Which means that this model, despite us trying to do the best we could, has significant issues trying to fit the data. I mean, if you cannot fit the training data, then there's no scope of doing well on your test set, right? So we want to see all the graphs in this talk is going to be how well we are doing on the training set. This is underfitting. We are trying to reduce underfitting, which is the number one symptom of a model with a high bias. So all the graphs will look like this, unfortunately, and we'll be measuring the error on the training set. Okay, so the baseline bidirectional model, which has about the same number of parameters, which is as big as that model, the bidirectional model, does significantly worse. So the traditional deep learning solution, which is the story of all end-to-end models, what people would do is try to blow it up, add more parameters, train a bigger model, see how well it does, right? You try doing that, it doesn't get you too far. You want to go to like 7 WER and you're still at 11. You're significantly far behind. So, what do you do? This is the conundrum.
Your times 2 is expanding which parameters?
Oh, so we increase the number of, here we increase the number of filters. We 2x the number of filters. Here we increase the number of neurons so that the final number of parameters is 2x of the baseline. The thing is, if you increase the number of neurons, the number of parameters increases by the squared of it. So you increase the number of neurons so that the number of final parameters is 2x the baseline model. The softmax remains the same, and the convolution is also basically the same. Cool. All right. Now we have all these choices, right? We know we have to do better. The literature has so many choices. In terms of convolutions, you can try all these different types of convolutions. There are so many different varieties of recurrent networks. There are so many different loss functions. Especially, all of these are sequence-to-sequence losses. You can train speech models with all of these. You can try improving your training by by normalizing better or finding different ways to speed up your training. There are also many different ways to normalize, but we are not so interested in that because you get into regularization when you're overfitting. Right now we are in an underfitting regime, right? We are not fitting the data as well. So there are multiple options there. We're not going to look into that. Okay, so what issues are, what assumptions is this model making? That's what we want to find out, and we want to address each point so that we can help fit the training data better and better. Okay. First, at the top layer, the CTC loss assumes that the characters, the predictions at different time steps, are independent of each other given the audio. This is an approximation of the label space. So what we want is a probability distribution over label space, right? CTC approximates it by making it, by factoring it and saying that P of L, let me find this, P of L as the product of PLT given X. This is not a full, this is an approximation, right? We'll get into why this starts biting you. Sorry, go ahead.
How much context do you put into the spectrum feature?
Oh, so we have a 20 millisecond window and we stride at 10 milliseconds. Right. So the convolutional layers, right? The convolutional layers will accumulate all this information from multiple time steps of the spectrogram. Yes. The receptive field of the spectrograms after 2 levels, not quite sure. I don't have it off the top of my head. Yeah. It should be about not more than 100 milliseconds, I think. Yeah. Yeah. Cool. Oops. Sorry. Okay. CTC makes this modeling assumptions. We'll get into why this becomes a problem. We want to fix it. Okay. Unidirectional RNNs also make a modeling assumption. It's implicit that it assumes I don't need to listen to the future at all when I'm trying to predict what the person is saying right now. Often what happens is when you train with CTC, these unidirectional RNNs learn to delay their output so that it will wait until it has enough future input and then output its prediction. We find out that this is not sufficient. If it were sufficient, then this curve, this gap wouldn't be so big. So there's an implicit assumption that the unidirectional RNNs are making that we want to remove. There's also assumptions made in the 2D convolutions. Despite doing mean and variance normalization and power normalization on the audio, we find that the fixed 2D convolution weights have a high variance of activations depending on how loud the audio is or how close the person is to the speaker, whether it's far field audio, whether there is noise, reverberation, all of these things. It turns out that the fixed weights encode an assumption that we want to try and remove. Okay, so in the rest of the talk, we'll look at each of these things. We'll see how we can relax the assumption that CTC makes. We'll see how we can make unidirectional RNNs include a little bit more information from the future. And we'll also see how we can do better input modeling. There's also a bonus item in here, which is, apart from all of these things, what else is preventing you from fitting your model, fitting your data as well? It turns out that your training mechanism also could be preventing you from fitting the training data as well as possible. So you also want to look at optimization tricks. We'll also see one optimization trick that we found to be really helpful in training this model. Okay, this is a really nice checkpoint before we get into the details of each of these points. If there are questions, I'm happy to take them now. Okay, all right, cool. Okay, let's get to this, the independence assumption that CTC is making. So if a person says, recognize speech using common sense, it's reasonable for an ASR system to say, oh, it could be recognize speech using common sense. It could also be recognize speech using common sense. The point is that it is reasonable for a model to want to output multimodal distributions. That is, it may want to pick 2 label sequences it thinks is likely, but nothing else. Let's see how CTC does this, right? So CTC predicts one character at a time. Okay? If you pick all the items from option 1, you get wreck a nice beach. If you pick all the items from option 2, you get recognize beach. But what CTC is doing is predicting one character at a time, independent of other characters at different time steps. So, for example, whether it predicts K here or not is independent of whether I predicted W here or not. So what happens is, if CTC wants to give equal probability to these two strings, recognize speech and recognize beach, it will have to give equal probability at multiple time steps. What happens is, you not only get these two strings, but also all combinations. If you pick some candidates from option 2 and some candidates from option 1, they also start having a non-trivial probability. So it's nearly impossible for CTC to have clean multimodal outputs without also giving probability to really junk transcriptions. We want to see how we can fix those. And this happens a lot, especially with things like Baidu. We have, when candidates come in for interview, we try to give them our speech recognition system and ask them to try it out. They often invariably say something like, I like the interviews I'm having so far at Baidu. Everything works so far until they say Baidu, and then our system almost always just transcribes it as BYDO. Simply because CTC, it's impossible for CTC to have a multimodal output. It assumes that all by and do's are spelled as BY and DO. And whenever you say Baidu, you will always spell it as BY and DO. And there's no way even a language model can try to fix it. I know what you're thinking. You're saying, oh, you should just use phonemes, right? Then BY and BAI are very similar. And DO and DU are very similar in phoneme space. That's true. There exists some transformation of the label space where this assumption is not so harmful. So, for example, if we were to do speech recognition instead of with characters, if we do it with word pieces, where we predict BY and BAI at the same time step, and DO and DU at the same time step, this problem isn't too hard or too problematic. And that's what Gram CTC is trying to do. Gram CTC, remember, has the softmax over the alphabet, right? Gram CTC's softmax is over the alphabet and also a whole bunch of n-grams. So you can have 1 gram, 2 gram, 3 gram, 4 gram, whatever. You can have a really large set as the softmax. And Gram CTC will try to infer the set of grams which makes sense, which it finds useful for modeling your training data. Does that make sense? Question? No, not quite. This is not quite at the language model. So you predict at each time step, instead of predicting one character, you predict multiple characters at a time, right? So here, at time step 1, you may predict one character, or you may predict one character, or 2 characters, or 3 characters. Okay, and then your probability of Baidu is just a product of 2 independent probabilities.
You lost one advantage of having characters, namely now you can't recognize all possible words because they can't be broken down into grams and bits.
Well, true. There's nothing stopping you from also including unigrams here. So this is a strict superset of CTC. So it shouldn't. It's true that if the model always chooses higher order grams to model things, and it almost never picks unigrams, then such a thing could happen. Yes. Oh, sorry.
Another advantage of the character-based thing that the vocabulary is so small. So you now you have many, many more labels, right? Doesn't that look parameter?
Yes, yes, indeed. But the side effect is, notice here you need 5 time steps to predict Baidu. Here you need 2 time steps to predict Baidu. So while the CTC cost calculation itself will become super expensive, you more than make up for it by running your RNNs much fewer.
And decoding time is the major bottleneck on the number of parameters that you're willing to use with that?
Yes, the decoding can also be approximated. Let's say you have 16,000, an output space of 16,000, right? You only need to take the top 100 or top 200, and then it'll be almost the same decoding time as a vanilla CTC. Question? True. You are not fixing the problem. It's still it's still approximating the label space. The best way to solve it is to not approximate it at all. This is simply finding a label space where the approximation hurts less. This is still an approximation. Yes. Okay, and gram CTC, just like how we saw CTC sums over all possible alignments, gram CTC enables speech recognition with word pieces by summing not only over alignments, but also over alignments and decompositions. That is, just like before, you need to provide the label, right? If it's cat, you just have to specify cat. You do not need to specify this is how you decompose cat. Just like earlier, you did not have to provide the alignment for the label sequence.
Meaning that if you allow all individual characters in your alphabet, then every word will have many decompositions, including the all characters.
That's true. Yes, yes. CTC often ends up, after training, picking one alignment and just putting all its weight on that. So similarly, once you have trained this model, gram CTC ends up picking one alignment and one decomposition and just saying, okay, I'm always going to decompose cat as CA and T, or just CAT, and just it'll stick with it. So this is trying to implicitly discover phonemes, if you will. That's how I think of it. Okay. I don't know if we need to get into the details of this. This is how you implement CTC. This equation, right? The first equation that you see. It becomes really expensive if you want to enumerate all of it, and dynamic programming gives you a clean way to calculate this first equation without incurring too much compute time. And if you want to do gram CTC, you simply add a couple more labels in there. That is, here we are in our softmax is over unigrams and bigrams. So you see CA and AT also, and there are a few more recurrence relations being added, and that's about it. That's basically the change. All right, how well did that work? It worked. It worked well in the sense that it got us it did as well as the 2x baseline with basically no increase in parameters. So we take the baseline model and remove CTC and instead do gram CTC with no increase in parameters, and we do as well as a model that includes that has twice as many parameters. By the way, this model is also either state of art or second on the Fisher switchboard challenge at this point. The word error rate on the word error rate is 7.3 for a single model on the switchboard set. Yeah, for a single model using only in-domain data.
Which model is the gram CTC?
Oh, the A model using gram CTC is. Yeah. So you can look at the gram CTC paper. Has more details about the experiments.
What's up? You're saying it's surprising that it's state-of-the-art for that, but you're saying here it's still just
Yeah. So the Fisher switchboard benchmark allows you to train non-deployable models. So if you take So if you take a bidirectional baseline and put gram CTC on it, it'll do better than this. And that is state of art, or second. Okay, so that's how we identified an issue, an assumption the model was making, and we fixed it, and it improved the model. Okay, the second thing is unidirectional models, right? There are so many ways also to fix this. Let's look at some of them. And this might be more familiar to many people here because the solutions are from actually invented here. The first figure, figure A, is the vanilla bidirectional model. There are two recurrences, one going forward in time, another going backward in time. And the bidirectional model incorporates both of those activations as you go deeper. If you want, now the problem, of course, is latency constraint, right? The reason why you cannot deploy this is because people want an output within 100 milliseconds of them having finishing speaking it. One thing you could do is to chunk up the audio into discrete time steps, discrete bunches called chunks, and just run bidirectional RNNs on each of those. But that's not so effective because RNNs typically need some warm-up. You need to unroll them a few time steps before they start, before the statistics of the RNN become more stable. Okay, so then what you could do is do what's in figure C. Figure C is basically it's the same as chunking, except the chunks are now overlapped. And there's some amount of work that is not used because you're spending some time just warming up your RNN. Of course, the discovery is you don't need to warm up your forward RNN because your forward RNN you can unroll infinitely anyway, and you only need to warm up your backward RNN. So this gets us to latency constrained bidirectional gated recurrent unit. It's quite a mouthful, so I'm going to call it LCB group. Okay. And the last one is the look-ahead convolution, which is kind of what we had already. You can think of it more or less as a 1D convolution that only has a receptive field to the right or to the future. Okay. So, okay, let's see what happens when you take a LCB GRU and try to deploy it. Just a couple of bits of information. What we call as chunk is the black dots. One chunk is a fixed length of time. Let's say 3 time steps in this case. Look ahead is the amount of burn-in you're giving into the RNN that you're going to throw away. And the sum of these two is what we call as context. People clear with this? Okay. Oh, sorry. Yes.
So what's the difference between, for the burning part, I'm not sure I understand. What does it mean to throw it away?
Yes.
Throw away the stuff that you saw on the back of the test?
Yeah. So I can. Okay. So in figure A, your backward RNN starts from time infinity. Here, you're resetting your backward RNN. So you start from ahead of the chunk and start from there. But you're only going to use these activations. The activations you calculated here, you're going to throw away. So that's why that's what I mean by saying you're going to start this backward RNN here, but whatever it produces in this time step, you're so not going to use.
The output of whatever else, the RNN, you're going to not
use
take
it.
those last two.
That's right. Yes, yes. This is mainly because your RNN needs some time for its statistics to become a little bit more stable. You can think of look ahead as wasted compute. You need it. It'll be wasted when training as well as during inference. Okay, so what happens? You can have. Okay, let's. There are 2 graphs here. One is measuring the serving latency. One is measuring how well it helps fit your data set. you can see that the model with the least latency is the forward-only model, which as soon as you get the audio packet, you can do its computation and return its output. You don't need to wait for anything. The one slightly above it, the red line, is the model with the look-ahead convolution or the convolution. Here, you can do convolution, and by the nature of convolution, it's not sequential, and you can do all time steps in parallel, and that adds only a small amount of latency on top of it. Once you start adding 1, 2, 3 LCB grooves, your latency starts stacking up a lot. Of course, at the very top green line is the bidirectional model, which is just non-deployable. You'll say something and you'll wait for like 1 minute or not 1 minute, 2 or 3 seconds before you get the output, right? The reverse happens in terms of accuracy. The bidirectional model has the least error rate, so this is the error rate actually on the dev set, but this is the same case on the train set also. The bidirectional model has the lowest error, and the more LCB grooves you add, the lower your error gets. And the more burn-in you give it, the closer the gap. You can imagine if the look-ahead is infinite, right? It's basically a bidirectional model. So that's what happens. Yes?
What's the difference between the 3 LC models?
Oh, so you remember in the forward-only model, there are 3 groove layers. You can replace 1 forward-only groove or two with 2 LCB grooves, or 3 forward-only layers with 3 LCB grooves. It's basically how many LCB grooves are in each model. Yes, when you have 3 and it has a very high look-ahead, it's almost the same as a bidirectional model.
So you were saying that if the look-ahead were infinite, then it would be a bidirectional model, but the latency is like, even at 25, is much lower than, the black's much lower than the green on latency, but it's getting close on the...
Yes. So you basically need...
20, I guess I'm just wondering what happens at 30 and 35.
Oh,
Latency, I mean, by the time it touches, is the black line up to the latency of the green line?
yes. We'll have to extrapolate. I haven't run the experiments, but that's what should be happening.
Because it looks linear there, but this line over here still looks way lower.
Yes. Right. What you could do,
Question about some details. So when you have one layer which looks ahead some number of frames, that's your latency. But if you have a second layer above that that does the same thing, then don't the latencies add up? How do you calculate your latency?
Yeah. So the latency is the last packet latency. So if I'm saying something after the last packet of my speech has been sent to the server, how much time does it take before I get the transcription back for it?
If each one had a 10-step look ahead and you stack 3 of them, your real look ahead.
Yeah. Yes. Exactly. Yes. Yes. It has that
And
effect.
what you're showing here is that you're not showing the per unit.
No.
You say 15,
No.
you mean-
This is the full model, like you said. Yeah. Yes. This is a stack of 3 back-to-back
When
LCD.
you do one layer and you say look ahead 15, that one layer can look ahead 15, but when you say 3 layers and 15, it means each layer looks ahead only 5.
Oh.
They're stacked, you're effectively looking ahead 15.
Oh, sorry. So I'm saying that for this yellow line, right, each of those layers has a look ahead of 15.
So your effective look ahead is even more.
It's much bigger. Yes.
So I really can't compare vertically between the black, magenta, and yellow lines.
True.
I should really compare this one.
Yes. Fair. Yes. That's a fair statement. Yes. Cool. Since the models basically look the same, you can take a bidirectional layer and try to run it as though it were a LCB group. This was the main push. This was the main reason why we wanted to try LCB groups, because we didn't want to train any new models. It turns out that's not helpful, in the sense that if you want to take a previously trained bidirectional model and run it as an LCB group, you'll need a really large look ahead. It's like 100 time steps, which is not functional. So no op there. But that helps. Adding, so in this model right here, we are adding only one LCB group. The black line, if you remember, shouldn't be. So we took this model, this black line, and set it to 20 look-ahead time steps, and we are measuring the number there. Okay, that also independently helps. At this juncture, I'm just looking at the time. I have about 15 minutes, and I have 2 more of these segments to cover. So I'm going to skip one of these, which is the per channel energy normalization, which is trying to say what is the issue you're having in modeling the input itself. Let's say there's some magic layer that we include that also helps. Perhaps not as much as others. But even on top of mean and variance normalization and power normalization, we found that PCN layers helped.
One more quick clarification.
Yes.
So at this point, you have one line for the gram CTC, one for the LCB.
Yes.
Does the LCB already have the gram CTC training?
No.
These are separately.
These are separate. Yes. Yes.
And same layers.
Sorry.
And they don't have yet.
Yes.
Well, eventually it's going to combine them.
Yes. Yeah, we are going to add it. Yeah. The point is we are trying to remove biases that are independently induced by different components of the system. So if we fix them independently, we should be able to add them, and it should compound. It will. Okay. The other thing which I often harp about, when you're running into underfitting like settings, what you not only want to look at is the size of your parameters and the biases it's inducing, but also are you running into optimization issues. It turns out that CTC is running into optimization issues in the sense that CTC is trying to infer both the alignment and the transcript, and it turns out to be a really hard problem for it to solve. So what we do is get alignment information from some model we have already trained. This is standard technique. And we try to pass this information using a cross-entropy loss. So now we have 2 losses, a CTC loss that is trying to magically infer the alignment, as well as a cross-entropy loss that is explicitly providing, say, here's the alignment. But the point is, it's just it's a really small weight on the cross-entropy loss. The train curves look like this. So if you were to train a CTC model from scratch, it does something like that. If you were to do cross-entropy training for like first 5 epochs and then start training with CTC, it jumps to a much lower regime. You could alternatively do joint training. That is, from the beginning, you have 2 losses, both the cross-entropy loss and the CTC loss, with some weighting for them. And it turns out that it really helps. So this is saying that if you're running into optimization issues also, you can see something like a really high error rate on the training set. So when you run into issues, also watch out for optimization problems. So if you take the baseline model and do pre-training or joint training, pre-training is pre-training with cross-entropy and then switching over to the CTC loss. Or if you do joint training, you use both the losses. Single-handedly, that's the single most important contribution for improving the error rate on the training data. Okay, now for combinations. Okay, so we combined the 3 losses so that we are adding no extra parameters. So we are on top of the baseline, we have CE, CTC, and gram CTC. So it's just more losses, which are either trying to fix optimization issues or trying to resolve the assumptions made by CTC, and that by itself easily fits the training data better than the baseline bidirectional model. This one is a little bit more of a confusion because the reason this, okay, if you combine all of these, right, if you add joint training and PCEN and LCB grew, and the other thing is IR augmentation. For far field audio and for audio inside closed environments, you want to, well, if your dev set has those kinds of audio, you want to do augmentation so that you are robust against those kinds of effects. So what we did was we also did IR augmentation. Unfortunately, the effect of that is that it changes your training data set, and that line is not comparable to the other items. But
did you measure the error of just the portion of the data training data that's common? Because I'm assuming that the blue has a bigger data set, of which the red one is a subset.
So we do IR augmentation during training on a large portion of the training data set. It's not extra data.
No,
It's
meaning
yes.
you still have the original, I suppose. You have the original
Yes.
plus.
Yes.
So did you measure the training error just from the original?
That's right. I don't have it.
Because
Yes.
I was thinking maybe the blue line is just on that training set and even that is higher. But you're saying no. I mean,
Yes.
I can understand why the union is higher because the other data is intentionally noisy.
Yes. It's we haven't run that
So the next
experiment.
chart, this little line next to it saying on the portion that's common to the other.
Yes. Yes.
And my gut feeling is even that might actually get higher
Oh.
because you have other. In other words, you have a broader footprint. So things which were not confusable earlier might now become confusable.
Oh. Perhaps. Maybe.
The sample in the training set, old training set, is
Yes.
not like anything else in the training set. Usually classified is now looking like a noisy example of something else.
Perhaps. I'm not sure
Yeah, I
if
don't know.
that'll
I mean,
happen.
that's why
It's for us to experiment and add another point there. Okay. So here's something more readable. So this is measuring both the train error and the dev error. The dev errors are much higher, mainly because the dev error are from a completely different distribution that does not match the training distribution. So so far we've been plotting this, right? The point is adding IR augmentation and all of these things also helps the final error rate. We tried also taking the baseline or 2x baseline and just adding IR, and it's still nowhere close to that kind of thing. Still, not claiming that this is a fair comparison, just also for sake of completeness, also providing the dev set numbers.
And what kind of features? You said this is some Baidu internal data.
Yes.
Okay, is it queries? Is it how long have you mentioned?
So for the English data set, this training data set contains data from a whole bunch of sources, wherever we could get training data from. So this has red speech. This has so this, for example, has speech from a public domain audio. For example, the White House releases transcribed audio, which you can use. So there's a lot of Obama speeches in here. In our training data set, and a whole bunch of sources wherever we could get training data. Yes.
And is it like a 5,000 hours?
So this is this is 10,000 hours. Yes. Yes.
And the test set is some standard, some deployment.
The test set is handpicked. There's some far field data. There's a whole bunch of names. There's some red speech. It's a mix of So
basically the kind of traffic you expect to see in deploys.
yes, we also the goal within the Baidu speech team is to solve speech, and we wanted a representative dev set. So if that number goes to 0, we can all go home. That's kind of. So we have a mix of a whole bunch of things. Yes. Yes.
In terms of other generic results, this is kind of the state of the art in deep speech.
Is this in deep speech?
Yeah.
Well, deep speech is an internal model.
I mean, speech isn't being run at
Oh, this is a very controversial question. On the public data sets, the model that uses only gram CTC, a bidirectional model that uses gram CTC, is up there. It's very close, highly competitive. We get 7.3 WER with a single model on a public benchmark using strictly public data sets. The best single model performance that I know of is 7.2. the best ensemble model that also uses data from external sources for text does way better. It's like 5 point something. So you can do way better. There's just really no way of deploying it. Okay, so the final model looks like this. The high-level takeaway is, if you want to fix a model that is underfitting, identify every source of bias and systematically go fix each of them. Also remember to find and fix optimization issues. That enables easier training. So for deep speech, we are able to fit the training data fairly well, and it's also generalizing reasonably. What's next? What if you want to generalize out of your training data? Let's say you want to start a new product, and you have no data from it. It may differ significantly in the types of things people say to the product. It may differ in for example, the input channel. It may be far field. It can be anything. How do you generalize outside of your training set? That's a much harder problem. That's next for us. Also, there's long-range transcription, multi-speaker speech, in-car, where you have everything together. You have far field, you have noise, you have accents, all of those things. Sorry, do you have a question?
No, I have a question.
Oh, okay, cool. All right. Plug here. If you want to try out the deep speech system, it's available as a keyboard. It's not the best keyboard. It's not the best keyboard in the world, but it's pretty good. You can do typing, of course. You can do swipe. It's a neural swipe system in here. And you can do speech to text. This is powered by deep speech. The deep speech model that is deployed on this app right now doesn't have all these improvements that we just talked about. So if you start using it now and like a few days later you notice a significant improvement, this is what is powering all those changes. Question? No, this is running on a server. Yes, it might start running on your phone too. Yes, true. Yes.
So I have another question.
This is it. Question time.
So some of the people is neural network business is that you really can't have an idea of how things work. So one of the ideas that people are pursuing now is not just really trying to understand the parameters, space, and construction, but rather the results. Just give you a piece of results where you don't want just characters. You want some attributes of what you really think is interesting, insights that you put there, and you train the machine to output also those outputs that is in the category, inside the categories that you want. Have you tried any of this to improve?
Yeah, so this one, right? We do a lot of error analysis on a regular basis. One of the biggest complaints that people in the academia have rightly pointed out, and we also see in our dev set, is proper nouns, is rare words that you have not seen in your training data. Example, Baidu. The word Baidu does not exist in, well, there are very, very few utterances in the training data. And it has a hard time generalizing it to audio that it has not seen. We also know that for far field, we are doing significantly worse. That's why we are doing per channel energy normalization and also IR augmentation. So we do a lot of error analysis. It's fairly manual. You have to understand, or you have to try and guess why the system is making a mistake on this particular audio clip. But yes, that is powering a lot of the next, the improvements on the system.
It is taken for time, but can you say very quickly what the per channel energy normalization is? Is the idea that you have these spectral bands,
yes,
and you're going to just normalize the energy for time?
Basically, yeah. So what we do two hand engineered things. One is power normalization using some Bayesian thing where we try to estimate what the power of the full. Yeah, this is the entire signal level. Then we also do the spectral normalization, mean and variance normalization from statistics collected from the training data. And then we do log compression of the spectrograms. What per channel energy normalization is trying to do is to automate both of or to parameterize both of these transformations. It removes the log compression and also tries to basically do automatic gain control, power normalization. Yeah. So XTF is the signal, is the value at the top, and T is time, F is frequency, and M is a running average of some form of the power you have seen in this frequency band for so long. And you try to normalize it so that it only picks up the peak of at each frequency.
The reason I asked you this is because I was thinking that if you do the normalization, it's often done in academic papers, you get Yakin's left,
Yes.
which has already reduces latency.
Exactly. Yes.
So you're just looking to see how you can.
Yes.
So it's averaging from the one side.
From one side. We used to do, we're still doing some Bayesian version of the power normalization where it's trying to estimate the power at when all the audio is present and continually updating its estimate and trying to do that, but this does a far better job.
Maybe a side question. He also commented about the Chinese speech recognizer. What kind of output tables do you have right now?
Yeah. So the architecture for the Chinese speech recognition system is also very, very similar to this. It's basically the same. The alphabet is just the Chinese alphabet. It has about 6,700. The alphabet is 6,700 in our case. And that's it. You basically train the system end to end, just like we do our English speech system. And it does. Chinese is somewhat easier to model this way because Chinese does not have the weird, I don't know if it has the weird orthography of the English language, where the same character can have multiple pronunciations and different combinations of characters can have, the same combination of characters can have different pronunciations in English, but I don't think in Mandarin that's that common. So it turns out to be much, much easier. And there are some products in Baidu which is being powered by this.
One more question about the signal thing.
Yes.
Do you explicitly extract pitch, or is the spectrum on?
No, we just only feed the spectrum. Yep.
All right, let's thank Sanjeev again.
Thank you. All right. Thank you.
Thanks.
Thank you. I'm glad you like it.